Hi everyone. This is going to be a short video subsequent to the halogenation of alkanes. So my plan here is to actually walk you through some of the problems that are in the textbook to give you an idea about how would you approach questions like this on an exam or a quiz. Okay, so let's look at something that's a solved problem. It's not a solved problem, it's an example in the textbook, and we will build from there. So what we've seen so far is, let's say if we have, and sorry, before I move on, I'm going to be using bond line structures now. I think I was using the condensed structural formula so far, but we're now going to translate all of that into a bond line structure and start using those for problems, because that's how you're going to see all these problems now. Let's look at what do we know. So this is all related to halogenation of alkanes. And before we get started, based on all of the other videos, the important thing that you have to remember is bromination is a selective reaction. Okay, bromination is a selective reaction, chlorination is not. Okay, so examples: propane. If we do a chlorination of propane, so let's say if you react it with Cl2, presence of heat or light, you're going to get two products. One's going to be 1-chloropropane. The other one is 2-chloropropane. And what we've seen previously is that the 1-chloropropane is formed in a 40% yield. 2-chloropropane is formed in a 60% yield. Okay. If we do bromination of propane, again, some sort of energy for doing this reaction. Get 1-bromopropane, 2-bromopropane. 1-bromopropane is formed in a 3% yield. This is formed in 97% yield. Okay, so look at the differences somehow. Okay, so that's why we're saying that bromination is a selective reaction. Now, I want to show you another example of this. So if we start with this molecule here, let's say that's the starting compound, and we do a chlorination on it. Now, one thing that I want you to realize and understand is right now, I'm writing the chlorine, the bromine, H nu or heat, these on the arrow. In my previous videos, I've put them on the side as plus. That really doesn't matter. What we're looking at here is the reaction of propane with chlorine. Now, whether the chlorine is on the arrow or it's here, that really doesn't matter, because depending on the source that you look at, there could be different conventions. Now, usually what we do is we write the reactants here, and any of the conditions, reagents, solvents, things like that, they go on the arrow. That's the convention. Okay, so in some sense, that's a reactant. The chlorine here is another reactant, or it could be treated as a reagent that we're using. So it's going up on the arrow. So, but do not get confused because of that. It doesn't matter where they show up. Look at your components. And again, also try to start generalizing these. Do not get the molecule stuck in your head. Don't think that this is something that's only relevant to propane. That's not how you view this. This is a propane is an alkane. So what we're talking about here is halogenation of alkanes. When this alkane reacts with chlorine, halogenation, these are the products that I get. When this alkane reacts with bromine, these are the products that I would get. Now, if you take this alkane now, So let's see, if we have this alkane here, what kind of hydrogens do we have? Okay, so notice how it has 3 methyl groups. So there are primary hydrogens. Any of the hydrogens on these methyl groups are primary. These are all CH3 groups. There's 9 of the primary hydrogens, and there is a tertiary hydrogen here. So that's the number of hydrogens we have. So we have 1 tertiary hydrogen, we have 9 primary hydrogens. So similar to propane, where we had primary and secondary hydrogens, we got a product corresponding to the primary hydrogens, product corresponding to the secondary hydrogen. So in this particular case, we should get these products. We have 2 kinds of hydrogens, we should expect 2 products. So we're going to get that, where the chlorine replaces one of the primary hydrogens. Okay, that's going to be 1 product. The other product that's possible is when the chlorine replaces the tertiary hydrogen. It turns out the ratios of these products, this is formed in a 35% yield, and this is formed in a 65% yield. Okay, so now you're actually getting the primary product as a major product, but also recognize that now we have more number of primary hydrogens. There are 9 primary hydrogens for 1 tertiary hydrogen. So if you think about it, 9 primary hydrogens combined, because if you replace any of those 9 hydrogens, you're going to get this product. 9 primary hydrogens combined gets you a 65% yield. 1 tertiary hydrogen gets you a 35% yield. So the reaction is still favoring the tertiary in some sense, like it's more favorable in terms of energetics. Okay, so that's the chlorination reaction. If I take the same molecule and if I do a bromination on this, turns out you get 0% of that, and you get almost 100% of that. So that is the only product. And so that is what we mean by bromination is a selective reaction. When there is a compound which has tertiary hydrogens and 9 primary hydrogens, that 1 tertiary hydrogen gives you 100% of the product. The 9 primary hydrogens do not give you, or almost do not give you, any product. So that's why bromination is selective. So the reason why bromination is selective, we went over that in a previous video. So please refer back to that. Okay, so that's where we went through the concept. So essentially what we see here is, okay, when you look at something like this, what I want you to gather from here, keep from here, is that whenever we do chlorination, these 2 examples, whenever we do a chlorination, we are going to get all possible products. Every hydrogen or every type of hydrogen in your compound is going to get chlorinated. It's going to get replaced by a chlorine. Okay, every position, every unique position in your compound is going to get chlorinated. But when we do bromination, we get very selective reactions. Okay, so the more substituted position, or the one that would result in a more stable radical, this is what we went over in the previous video, the position that would result in a more stable radical, which is usually the more substituted position, that gives you the major product, sometimes almost exclusive product. This is also almost exclusive, like 97% is almost like 100%. So you get like very complete reaction there. So having that, now let's apply this to like other molecules. Okay. Okay, so one of the examples we have here is this molecule, and we'll try to do a bromination as well as a chlorination on this molecule to basically show you what kind of products are. So let's say if this is the molecule I have, and you have to do a chlorination. So once I get the molecule, the first thing that you want to do is identify all the unique positions in this molecule, like how many unique hydrogens are there in this molecule. So if you look at it, this is a methyl group, this is a methyl group, that's a methyl group. They're all connected to that same carbon. So I would say this is one unique position. They're all the same, basically, okay? So it's basically one. They all are similar, identical. There's no hydrogen here because that's a quaternary carbon, 4 bonds to it. This is a secondary carbon. So this is another position because it's different from that one. This here is a tertiary carbon. It has 1 hydrogen on it. There are 2 hydrogens here. So this is primary. This is secondary, tertiary. And then we have primary here. Now, are these methyl groups the same as these methyl groups? Although they are all methyl groups, I would say no, because these methyl groups are all connected to a quaternary carbon, but these 2 methyl groups are connected to a tertiary carbon. So they're not exactly the same. So that's going to be another position. So there are hydrogens on all of these positions. So that means when we do a chlorination of this molecule, we're going to get all of these products. Okay, we're going to get 1 chlorine here, plus I'm going to get a chlorine at that tertiary carbon. Chlorine at the secondary carbon. And you're going to get a chlorine at that methyl. So 4 products would be possible. Now, what are their ratios? We cannot just basically come up with that with those numbers or the ratios. So we don't have to bother about that. But all of these products are possible. Okay, so 4 possible products. Now, if you take the same molecule and we do a bromination on it, bromination is a selective reaction. So now we're going to have a major product, okay? Not every product is going to form. That's what we saw in the examples that we just noticed. So there is a primary position, secondary position, and tertiary position. So the major product from bromination is going to come from this tertiary position because that's the one that's going to give us the most stable radical. So for bromination, we can actually write this as the major product. Okay, it would be favored over a secondary also. Now, what would be the ratio of the tertiary to the secondary? I do not know that. We cannot come up with those numbers, but bromination would give us a major product. Hopefully like 60–70% of the reaction mixture is going to be this tertiary product. Okay, probably more. Okay, is going to be that tertiary product. So whenever we do brominations, we can always think about one major product. But in a chlorination, we cannot say what is the major product. I mean, it's really hard because it would always give us like a mixture of several products. Okay, so that's one thing to remember. The other important thing based on the mechanism, or maybe we'll do like one more example quickly. So let's say if we have that molecule, it's a cyclohexane with a methyl group now. If we do a chlorination, H nu or heat, by looking at that molecule, what I can see is that this is a unique position. This is primary. This is a unique position, tertiary. and then we have a bunch of secondary positions. Now, these secondary positions are not all similar, they're not equivalent. So they could give us like separate products. Okay, they would all give us like separate products because this secondary position is closer to that tertiary carbon. This is not as much, so based on that. So essentially what's going to happen is when we do the chlorination here, you're going to get that. Going to that. And this. Those would all be the products. Now, these two positions are identical. That's why I'm not putting whether I put the chlorine here or there, it's the same. And the same is true for these two positions. They are identical. That's why we don't have to draw the chlorine here and here and here and here. We don't have to do that. They're the same product. And you can test that by naming it. If you name that compound versus this compound, they have the same name. Okay, so that would be all the chlorination products. If we go to a bromination, from this reaction, we can expect one major product, which is going to be that, because that's the tertiary position. Okay, so that's something to keep in mind as you're working on problems. And whatever we are doing here, the next chapter, chapter 7, builds on this content. So it's very important to like understand this material here. Okay. Now, the other thing about free radical halogenation is when you have an example like this. Let's say if you take this molecule and if you do a bromination on this, HNu or heat. And we'll talk about bromination mostly because bromination is the selective reaction. Chlorination gives us mixtures of products. So when we are doing something in the lab, we don't do chlorinations often. It's a bromination that's usually done. Okay, so bromination of this. Now, for this particular molecule, notice how this has a primary carbon and there is a secondary carbon. Okay. Now, this is also secondary, but it's identical to this secondary, and that primary is also identical to this primary. So there are only two unique positions in this molecule. So that means when we do this reaction, our product, the major product, should be this compound. This is the major product. But notice that this carbon is now chiral, which means it can have two enantiomeric possibilities. Okay, it will have two stereoisomers. There's one chiral center, so two stereoisomers are possible. So which one is actually formed? Is it R? Is it S? Is it both? Do we get a racemic mixture? What happens here? That's something very important. And now the answer to that, again, lies in the mechanism. Mechanistically, what's going to happen is this compound is going to become a radical at some point. Okay, it's going to become a secondary carbon radical. And I would encourage you to work through the mechanism for this reaction so that you actually see how this product is formed. Okay, so you're going to get to this radical. And this radical is what becomes a product later. Now, this radical here, secondary radical, okay, there's a hydrogen over there. This radical is sp2 hybridized. And we talked about this in the video on carbon intermediates. This is sp2 hybridized. That means it's a planar structure, okay? And what that means is the bromine can add from both faces of the trigonal plane. Okay, this is a flat molecule, and when the bromine is added, it can add from the top face or it could add from the bottom face. And so what that means is when you get to this product, you are always going to get this plus its enantiomer. Okay, you're always going to get that. Well, in this product, I don't have anything shown, so maybe I can put this on a wedge now. And so we're going to get this plus the enantiomer. Okay, now an easy way to say this is to draw the molecule with a squiggly bond. So it's not a dash, but it's a squiggly line. Okay, so something like that, a squiggly line, not a dash bond. So that squiggly line implies that this bond is a wedge, or it can be a wedge and a dash. And by doing that, we are implying both enantiomers, because if it's a wedge, it's one enantiomer. If it is a dash, it's the other enantiomer. The squiggly line captures both. Or you might see plus minus written next to it, which basically means it can be both enantiomers again. It has the plus optical activity or the negative optical activity, okay? So that's something to keep in mind when you're working through these problems, the homework. Okay, thank you.